Right now, as you lie there listening to this, something almost impossible is happening inside you. Not once in a while, not every few minutes, not only when the sun is bright overhead. It is happening continuously, without pause, without sound, without any sensation at all. Every second, an immense flood of particles is streaming outward from the sun, crossing the emptiness of space, reaching Earth, passing through its crust, its oceans, its cities, its mountains, its buildings, and then moving through your body as though none of it were there. They do not knock into you in any way you can feel. They do not warm your skin. They do not leave a trace behind that your senses could ever notice. They arrive, pass through, and continue on, disappearing into the dark on the far side of the planet. These particles are called neutrinos. And the first strange thing about neutrinos is not that they are exotic. It is not that they come from stars. It is not even that they are difficult to detect. The first truly strange thing is that they are everywhere, all the time, and yet the material world barely seems to register their existence. It is a remarkable thought. The solid earth beneath you feels permanent and resistant. Your body feels substantial. Matter seems reliable, tangible, unavoidable. And yet, for neutrinos, almost all of that solidity means almost nothing. They pass through rock, steel, water, and flesh with astonishing ease, as though the everyday world were mostly empty. That alone would already make them mysterious. But the deeper mystery begins with something even more unsettling. Physicists did not first discover neutrinos by seeing them. They discovered them because something was missing. In the early 20th century, scientists were studying radioactive decay, especially a process called beta decay. In this process, a nucleus changes internally and emits an electron. On paper, it seemed simple enough. Measure the energy before the decay. Measure the energy after. Compare the two. Physics had already built its trust on a principle so basic it seemed almost untouchable. Energy cannot simply vanish. That rule had survived every test. It held in collisions, in heat, in motion, in chemistry, in mechanics. It was not treated as a rough guideline. It was treated as one of the deepest truths in nature. But beta decay created a problem. When physicists measured the electron that came out of the nucleus, its energy did not match what it should have been if only the visible products of the decay were involved. Sometimes the electron carried more energy, sometimes less. The amount missing changed from one event to the next. It was not a fixed error. It was a shifting deficit. That was deeply disturbing, because if the measurements were right, then one of two things had to be true. Either energy conservation, one of the most trusted principles in all of physics, was quietly failing inside atomic nuclei, or something else was escaping the decay unseen, carrying away the missing energy. That second possibility was extraordinary. It meant that every time one of these decays happened, another particle might be leaving the nucleus alongside the electron, invisible to every instrument of the time, untouched by the detector, carrying away exactly the energy needed to restore the balance. In 1930, Wolfgang Pauli proposed that this was what must be happening. He did not make the proposal with confidence or dramatic certainty. In fact, he famously described it almost apologetically as a desperate remedy. That phrase matters because it tells you just how uncomfortable the idea was. He was suggesting that a completely unseen particle existed not because anyone had observed it directly, but because the mathematics of a missing energy balance seemed to demand it. The neutrino entered physics first as an absence, not as a flash in a detector, not as a bright new line in an experiment, not as a visible track through a chamber. It appeared as a hole in the accounting, a gap in the numbers, a small but stubborn violation that could be repaired only if something ghost-like was slipping away unnoticed. That is one of the most beautiful patterns in science. Sometimes nature does not reveal itself by what it shows us. Sometimes it reveals itself by what refuses to add up. And that is where the neutrino begins, as a hidden answer to an invisible question. Imagine the boldness of that moment. A scientist looks at a process happening inside matter and says, in effect, I cannot see the missing thing. I cannot catch it. I cannot measure it directly. But something real must be there, because the universe is still obeying its own rules. That is what made the neutrino so compelling from the beginning. It was not invented casually. It was pulled into existence by the refusal of physics to let the books remain unbalanced. And yet, the proposal created a new mystery immediately. What kind of particle could carry energy and momentum out of a nucleus and still leave no mark in the apparatus? What kind of thing could be created in enormous numbers and still remain almost completely hidden from matter itself? That question would take decades to answer, because once the neutrino had been proposed, physicists faced a startling possibility. The universe might contain particles that are not rare at all, not distant, not confined to extreme places, but abundantly present and almost impossible to notice simply because they interact so weakly with everything around us. A hidden population flowing through the world continuously. A silent rain from the sun. A stream through your body at this very moment. And tonight, as we begin tracing the neutrino story, that is the image to hold in mind. Not a violent explosion, not a giant machine, not a faraway galaxy, just the quiet fact that while you rest here in the dark, trillions upon trillions of neutrinos are passing through you, through the walls around you, through the ground below you, and onward into the night, carrying with them one of the strangest stories modern physics has ever uncovered. To understand why neutrinos are so elusive, it helps to let go of one of the most natural pictures we carry about particles. Most people, quite reasonably, imagine a particle as a tiny object, a minuscule bead, a microscopic speck moving through empty space, the way a grain of dust drifts through sunlight. That image is useful for a first impression, but it begins to fail once you move deep enough into modern physics. At the scale where neutrinos live, a particle is not best understood as a little solid thing. It is better understood as a disturbance in a field. And a field is a very different kind of reality. A field is not an object sitting in one place. It is something spread throughout space. Temperature is a simple example. In a room, temperature is not located at one point, like a coin on a table. It exists throughout the room. At every place, the air carries some value of temperature, even if that value changes from one corner to another. Modern physics says something similar about the basic ingredients of the universe. Space is not empty in the way common sense suggests. It is filled with fields. The electron field, the electromagnetic field, the quark fields, and among them, the neutrino field. A particle is what happens when one of these fields is excited in the right way. Not a tiny marble moving through emptiness, but a traveling ripple in something that is already everywhere. Think of a still pond. If you drop a stone into the water, a ripple spreads outward. The ripple is not a separate object added to the pond. It is a pattern moving through the water that was already there. The water remains the deeper reality. The ripple is something the water does. That is much closer to what a particle is. A neutrino is not best pictured as a tiny hard pellet slipping through atoms. It is a traveling excitation of the neutrino field, a moving pattern in something woven into space itself. And once you see it that way, a new question appears. Why does this particular field interact so little with everything else? Because that is the real secret behind the neutrino's ghostly behavior. It is not about the neutrino being especially small in some ordinary mechanical sense. It is not just that it is light, or fast, or hard to aim at. The deeper reason is that the neutrino couples very weakly to the fields that make up ordinary matter. In physics, coupling means connection. It means one field has a way to influence another. Some fields are deeply entangled with each other. Electromagnetism, for example, is everywhere in daily life. Light is electromagnetic. Chemistry is electromagnetic. The solidity of matter, the reason your hand does not pass through a table, is electromagnetic. The attraction of electrons to nuclei, the repulsion of one charged surface from another, the reflection of light off objects, the structure of atoms, the behavior of electricity in wires. All of it depends on electromagnetic coupling. That force is loud. It grips matter constantly. It shapes almost everything you have ever directly experienced. The neutrino, however, carries no electric charge, so the electromagnetic field has almost no hold on it at all. Light does not push it around in the ordinary sense. Electric fields do not deflect it. Magnetic fields do not bend its path. The vast electromagnetic activity that fills the visible world barely touches it. This is one reason neutrinos can move through matter so effortlessly. When you touch a wall, it feels solid because the electrons in your hand and the electrons in the wall repel each other. The atoms never truly merge. Electromagnetic forces keep them apart, creating the sensation of contact and resistance. But a neutrino does not respond to that same barrier. The structure that makes matter feel firm to you does not present the same obstacle to a neutrino. It continues, almost undisturbed. The strong nuclear force does not help much either. That force binds quarks together inside protons and neutrons. It is extraordinarily powerful, but it acts only on particles carrying the right kind of charge for that interaction, something called color charge. Neutrinos do not carry that property, so the strongest force in the atomic world also mostly ignores them. That leaves only two forces with any relevance at all: gravity, which technically acts on anything with energy, and the weak nuclear force. Gravity, though universal, is far too faint at the particle scale to matter in normal neutrino detection. So in practical terms, nearly everything we know about neutrino interactions comes through the weak force. That name is not poetic, it is literal. The weak force is genuinely weak compared with electromagnetism and the strong force, especially at the energies involved in most neutrino processes. And because neutrinos rely almost entirely on this one delicate channel of interaction, they slip through matter with astonishing ease. This is what physicists mean when they say the neutrino is weakly interacting. They do not mean it is shy. They mean the universe itself gives it very few available ways to collide, scatter, or announce its presence. Imagine a crowded room where countless conversations are happening at once. Most people in the room speak languages that overlap enough for interruptions, responses, reactions, and misunderstandings. There is constant exchange. But now imagine someone moving through that same room. speaking a language almost no one else understands. They are present. They are real. They occupy the same space. But almost none of the conversations connect to them. That is something like the neutrino's relationship to ordinary matter. It shares the same universe. It passes through the same spaces. It overlaps with atoms, stars, planets, water, skin, air, stone. But the rules that allow interaction are so limited that almost all of those encounters amount to nothing. This explains why it took so long to detect one directly. By the mid-20th century, physicists had a strong theoretical reason to believe neutrinos existed. The energy accounting in beta decay made sense if they did. Enrico Fermi had built a mathematical framework that described their role in radioactive decay and gave the particle its name, neutrino, meaning little, neutral one. The theory worked beautifully. It explained the shape of the measured energy distributions. It turned a mystery into a coherent picture. But a theory is not the same thing as a direct detection. To actually catch a neutrino, scientists needed an enormous number of them and a detector large enough, patient enough, and sensitive enough to wait for one of the incredibly rare moments when a neutrino would finally interact. That moment came in 1956. Clyde Cowan and Frederick Rons placed a detector near a nuclear reactor, one of the most intense man-made sources of neutrinos available at the time. A reactor produces an immense flood of them, a torrent of invisible particles pouring outward every second. By positioning the detector close to that source, they maximized the chance that at least a few neutrinos might interact inside it. Even then, the rate was tiny. That is the part worth pausing over. It was not that neutrinos were scarce. They were abundant beyond imagination. The problem was that they simply refused, almost always, to do anything detectable. Cowan and Ron were not trying to find a rare particle that showed up only occasionally. They were trying to catch one interaction out of an overwhelming sea of particles flowing past almost without consequence. And when they finally succeeded, it confirmed something profound. The neutrino was real. Not only as a mathematical necessity, not only as a missing term in an equation, but as a genuine physical presence, streaming from reactors, from radioactive decays, from stars, from the cosmos itself. A particle that had first appeared as a hole in the bookkeeping had now been caught touching matter, however briefly, however rarely. That changed physics forever. Because once neutrinos were known to be real, the question was no longer whether they existed. The question became, what kind of universe allows something so abundant to remain so hidden? What does it mean that one of nature's basic particles can pass through entire planets almost untouched? What does it mean that matter, which feels so full and substantial to us, can be almost transparent to something produced in unimaginable numbers? And what else might be true about reality if the visible, tangible world is only one layer of a much deeper structure of fields and interactions, most of which we never notice directly? The neutrino forces those questions on us. It quietly tells us that visibility is not the same as importance, that detectability is not the same as abundance, and that the universe may be filled with processes so weakly connected to our senses that they could surround us for centuries before we learn how to notice them. So tonight, the neutrino begins to take on a different shape in the mind, not just a missing particle from an old nuclear puzzle, but a whisper from the architecture of reality itself. A ripple in a field, a traveler almost untouched by light, charge, and ordinary matter. A particle so detached from the familiar machinery of the world that even now, as countless billions cross the room around you, the universe gives you no direct hint that they are there. If neutrinos were only difficult to detect, they would already be fascinating. But what makes them truly extraordinary is that there is not just one kind of neutrino. There are three. And this is where the story begins to move from mysterious into deeply strange. In ordinary life, identity feels simple. A thing is what it is. A cup is a cup. A stone is a stone. A person remains themselves from one room to the next. Even in much of physics, particles seem to carry this same stability. An electron is always an electron. A proton remains a proton. Their identities appear clean and fixed. Neutrinos do not behave that way. To see why, we first have to understand a concept physicists call flavor. The word sounds playful, almost casual, but in particle physics it has a very precise meaning. Flavor is not about taste or texture or anything sensory. It is a label, a category of interaction, a way of identifying which family a particle belongs to when the weak force is involved. Neutrinos belong to a larger family of particles called leptons. That family includes three charged particles you may have heard of, at least one of them very intimately: the electron, the muon, and the tau. The electron is familiar. It lives in every atom. It shapes chemistry, electricity, light emission, and much of the visible structure of matter. The muon is like a heavier cousin of the electron. In almost every measurable way, it behaves similarly, but with far more mass. The tau is heavier still, another version of the same general pattern and an even larger mass scale. And each of these charged particles has a neutrino partner. The electron has the electron neutrino. The muon has the muon neutrino. The tau has the tau neutrino. These are the three neutrino flavors. Now, at first glance, this may sound like a tidy classification. Just three related particles, each paired with a charged cousin. But the pairing matters much more deeply than a simple naming system. The weak force treats these pairings with extraordinary precision. When certain nuclear reactions occur, or when particles decay through the weak interaction, the neutrino that appears is not arbitrary. If an electron is involved, the neutrino produced is specifically an electron neutrino. If a muon is involved, it is a muon neutrino. If a tau is involved, it is a tau neutrino. The weak force does not mix these labels carelessly. It keeps track of them with exactness. That means flavor is not just a descriptive tag. It is built into the rules of what interactions are allowed to happen. And for a long time, physicists believed that was the end of the story. Three flavors, three identities, three distinct neutrinos, neat and orderly. But nature had something much stranger in mind, because although neutrinos are produced and detected with a definite flavor, they do not travel through space in a way that preserves that flavor cleanly. This is one of the most astonishing facts in all of modern physics. A neutrino can be born as one flavor and later be detected as another. An electron neutrino created in the Sun can leave the solar core as an electron neutrino and arrive at Earth with some chance of being measured instead as a muon neutrino or a tau neutrino. The same particle, same journey, different identity at the end. And if that sounds impossible, that is because by ordinary intuition, it should be. We are used to the idea that things remain themselves while they move. A red ball does not roll across a room and become blue halfway there. A violin note does not travel through the air and quietly become a flute note. before reaching your ear. Identity in the everyday world feels stable, but neutrinos live under quantum rules, and under those rules, identity can become something more fluid than common sense allows. To understand how, it helps to make a subtle but very important distinction. Flavor is not the same thing as mass. That sentence seems harmless at first, but it opens a door into one of the most elegant and unsettling structures in particle physics. Flavor tells you how a neutrino participates in weak interactions. It tells you which charged lepton it is associated with. It is the label the weak force reads. Mass tells you something different. Mass governs how the neutrino propagates through space and time. It shapes how its internal quantum phase evolves as it moves. Those are two different kinds of description. A simple analogy helps here. Imagine describing a person in two completely different ways. You could describe them by their name, which tells you who they are socially, which messages are meant for them, which relationships belong to them, which doors open when they arrive. Or you could describe them by their weight, which tells you how gravity affects them, how difficult they are to lift, how they move physically through the world. Both descriptions are true. Both refer to the same person, but they answer completely different questions. Knowing one does not automatically tell you the other. That is roughly the relationship between flavor and mass for a neutrino. Flavor is like the name. Mass is like the weight. And the strange thing about neutrinos is that those two descriptions do not line up neatly. For most particles, they do. An electron has a definite identity and a definite mass, and those descriptions point cleanly to the same thing. There is no confusion, no mismatch. But for neutrinos, the flavor states and the mass states are not the same. That means an electron neutrino is not a particle with one single clean mass attached to it. Instead, it is a quantum combination of several underlying mass states. This is where the story becomes beautifully weird. When a neutrino is produced, say inside the sun, it is created with a definite flavor because the weak force requires that. But the neutrino that emerges is not traveling through space as one simple, mass-defined object. It is actually a superposition, a quantum blend of multiple mass states layered together. And those mass states do not evolve at exactly the same rate. That is the crucial detail. They move together, but not perfectly in step. A useful way to picture this is through music. Imagine three musicians playing the same note at the same moment. At the beginning, the sound blends beautifully into one unified tone. It seems like one thing. But if each instrument is tuned just slightly differently, then over time, their phases drift apart. What began as one clean sound slowly changes in character. It becomes richer, stranger, slightly different, even though no new note was introduced from outside. The sound changed because the underlying components slipped out of sync. That is essentially what happens inside a traveling neutrino. The different mass components begin together, synchronized in exactly the combination that the weak force recognizes as, say, an electron neutrino. But as the neutrino moves, each mass state accumulates quantum phase at a slightly different rate. The combination shifts, and once the combination shifts, the flavor identity shifts with it. The neutrino has not been struck by anything. It has not collided with a particle and transformed. Nothing external had to happen. It changes because the internal structure of its own quantum state evolves naturally over time. This phenomenon is called neutrino oscillation, and it is one of the most extraordinary discoveries in modern science. A neutrino can oscillate from one flavor into another simply by traveling. That means the label attached to it at birth is not permanent. Flavor is not a fixed essence. It is a temporary arrangement of deeper components that do not remain aligned forever. This would already be philosophically remarkable, but in physics, it carries a much sharper consequence. Oscillation can only happen if neutrinos have mass. That point is critical. If all the underlying mass states were identical, or if neutrinos had exactly zero mass, then those internal phases would remain locked together. The flavor composition would never drift. An electron neutrino would remain an electron neutrino forever. No oscillation would occur. But oscillation does occur. It has been measured repeatedly, precisely, across different experiments, different sources, different distances, different energies. And that means the neutrino is not massless. That conclusion sounds simple, but it was revolutionary, because for a long time, the standard model of particle physics, our most successful framework for describing the subatomic world, treated neutrinos as massless, not approximately massless, exactly massless. Neutrino oscillation proved that assumption was wrong. And so the neutrino, once introduced as a hidden patch to preserve energy conservation, had now done something even more disruptive. It had exposed a crack in the deepest and most successful theory of matter we possess. This is part of what makes neutrinos so compelling. They are not just hard to catch. They are not just abundant and elusive. They are not merely weird little particles streaming out of stars. They are messengers from a layer of reality where the categories we depend on, identity, mass, interaction, stability, do not fit together in the way we expect. A neutrino is born with one name and can arrive with another. Not because it forgot what it was, but because what it was turned out to be more fluid, more layered, and more quantum than the visible world ever prepared us to imagine. And as you rest here listening, it is worth pausing on just how astonishing that is. The sun may be sending us particles that begin their journey with one identity and end it with another. A quiet, shape-shifting stream crossing space in total silence. Invisible travelers, changing character in the dark between the stars. As a neutrino travels through space, something deeply unusual happens. It does not remain exactly the same, not because it collides with something, not because it gets damaged, not because space itself is slowly altering it from the outside, but because the way a neutrino is built at the quantum level is not as fixed as it first appears. A neutrino can be created with one identity and later be detected with another. That is not a metaphor. It is a measured physical reality. An electron neutrino born in the core of the sun can leave the sun as an electron neutrino and arrive at Earth with a real chance of being measured instead as a muon neutrino or a tau neutrino. The same particle. One journey, different identity at the end. That sounds impossible if you picture a particle as a tiny object with one permanent label attached to it. But neutrinos do not behave like simple little objects. They behave like quantum states. And quantum states can be layered. When a neutrino is created, the weak force gives it a definite flavor. That part is sharp and exact. But underneath that flavor identity is a deeper structure made of different mass states mixed together. And those mass states do not evolve at the same pace. They begin aligned, but they do not stay aligned. A calm way to picture this is to imagine three soft tones being played together as one note. At first, they blend perfectly, but over time, each tone drifts just slightly out of step with the others. The overall sound slowly changes, even though nothing external touched it. That is what happens to a neutrino. Its internal components drift out of sync as it moves. And because flavor depends on the exact way those components combine, the neutrino's flavor changes too. This is called neutrino oscillation, and it means that neutrinos do not carry identity in the rigid way we normally imagine. Their identity is more like a temporary pattern than a permanent label. That alone would make neutrinos extraordinary. But oscillation also reveals something even more important. It proves that neutrinos have mass. Because if all the mass components were identical, or if neutrinos had no mass at all, they would stay in perfect lockstep forever. The flavor would never rotate. The oscillation would never happen. But it does happen, and that means the neutrino is not massless. That single fact changed modern physics. Because for a long time, the best theory we had, the standard model of particle physics, assumed neutrinos had exactly zero mass. Neutrinos turned out to disagree, and so once again, the neutrino did something remarkable. It did not just hide from detection. It quietly revealed that one of our deepest theories was incomplete. For many years, the sun appeared to be missing neutrinos. That sounds impossible, because neutrinos are one of the main products of the nuclear reactions happening deep inside the sun's core. If our models of the sun were correct, then a huge number of electron neutrinos should have been arriving at Earth every second. And they were arriving. Just not in the numbers physicists expected. One of the most famous experiments in this story took place deep underground in South Dakota, in a gold mine nearly a mile below the surface. There, physicist Raymond Davis Jr. built a detector using a huge tank filled with cleaning fluid. It was not glamorous, it was not futuristic, but it was designed to do one very specific thing: catch rare interactions from electron neutrinos coming from the sun, and over time, it did detect them. But there was a problem. It only saw about a third of the number it should have seen. That discrepancy lasted for years, then decades, and that is what made it so unsettling. If the detector was working, then maybe our models of the sun were wrong. But if the solar models were right, then maybe something was happening to the neutrinos on the way to Earth. For a long time, no one knew which possibility was the real one. And that uncertainty mattered a lot, because if our model of the sun was wrong, that would shake our understanding of how stars produce energy. But if the neutrinos were changing somehow during flight, then the problem was even stranger. It would mean the particles themselves were behaving in a way the standard model did not properly describe. Eventually, the answer came from a better kind of detector. A detector that could see not just electron neutrinos, but all neutrino flavors together. And when those later experiments finally measured the total neutrino flux from the sun, the missing neutrinos were not missing at all. They had simply changed flavor during the journey. The sun had been producing the correct number all along. The Earth was just receiving many of them in forms the older detector could not see. That was one of the most elegant scientific resolutions of the modern era. A decades-long mystery, solved not because the sun was wrong, but because the neutrinos were stranger than expected. They had left the sun as one thing and arrived as something else. And that discovery helped confirm one of the deepest truths about them. Neutrinos do not simply travel. They evolve. The solar neutrino mystery did more than solve a missing particle problem. It forced physics to accept something it had not wanted to accept. Neutrinos must have mass. Not much, almost unimaginably little, but not zero. And that matters because, in modern physics, Mass is not just a number attached to a particle. Mass changes how a particle moves through time. It changes how its quantum state evolves as it travels. That is exactly why neutrino oscillation is possible. If neutrinos had no mass, or if all their mass states were perfectly identical, then the internal parts of the neutrino would stay synchronized forever. The flavor would remain fixed. An electron neutrino would stay an electron neutrino from the moment it was created until the end of time. But that is not what happens. The flavor rotates. And the only way that rotation can happen is if the underlying mass states evolve at slightly different rates. That means the neutrino carries real mass differences inside its structure. This was a major shock because the standard model of particle physics had treated neutrinos as exactly massless. Not approximately, not close enough, exactly zero. That prediction was not random. It came from the way the theory was built. And for most particles, the standard model had been astonishingly successful. It predicted particles before they were discovered. It described interactions with incredible precision. It had earned trust at a level few scientific theories ever achieve. So when neutrinos disagreed with it, physicists paid attention. This was not a tiny detail. This was a sign that the theory, as powerful as it is, does not tell the full story. That is one of the reasons neutrinos matter so much. They are not just weird particles from stars and reactors. They are evidence that the deepest framework we have for matter is incomplete. A tiny crack in an otherwise beautiful structure. And strangely enough, that crack came from one of the lightest, quietest particles in the universe. Not from something huge or violent, but from something almost invisible. To understand why neutrino mass was such a big problem, we need to look at how particles normally get mass in the first place. In the standard model, mass does not just appear automatically. Particles get mass through their interaction with the Higgs field. The Higgs field fills all of space. It is not a force in the usual sense, but more like a background condition of reality itself. And when certain particles interact with it in the right way, that interaction shows up as mass. That is how electrons get mass. That is how quarks get mass. That is how much of the visible structure of matter becomes possible. But the neutrino creates a problem, because in the original standard model, the neutrino was only included in a left-handed form. That phrase sounds strange, but in particle physics, handedness has a very specific meaning. It refers to the relationship between a particle's spin and the direction it is moving. And for neutrinos, the weak force only sees the left-handed version. That by itself would not necessarily be fatal. But here is the issue. For the Higgs field to generate mass, it normally needs to connect a particle's left-handed and right-handed versions together. That connection is what produces mass. Electrons have both. Quarks have both. Neutrinos in the original standard model did not. So the bridge could not form. There was nothing for the Higgs field to connect the neutrino to. And if that connection cannot happen, the standard model predicts the neutrino's mass must be exactly zero. Not small, not difficult to measure. Zero. But experiments proved that zero is wrong. That is why neutrino mass is not just a measurement update. It is a structural problem. It means the theory is missing something important. Either there is a right-handed neutrino the standard model does not include, or neutrinos get mass through some deeper mechanism entirely, and both possibilities point beyond the standard model. That is what makes neutrinos so powerful. Scientifically, they are one of the clearest signs we have that our best theory is not the final one. Handedness sounds like a simple word, but in particle physics, it points to something surprisingly deep. A particle can spin, and that spin can be oriented relative to the direction the particle is moving. If the spin points one way, we call it left-handed. If it points the other way, we call it right-handed. For everyday objects, this does not sound especially dramatic. But for particles, it changes everything, because the weak force, the only force that really interacts with neutrinos in a meaningful way, has a built-in preference. It does not treat left and right equally. It only couples to left-handed particles and right-handed antiparticles. That is one of the strangest asymmetries in all of physics. For a long time, scientists assumed nature would not fundamentally care about left versus right. It felt too arbitrary, too human, too geometric to be built into reality itself. But in the 1950s, that assumption was tested, and nature failed the symmetry test. Experiments showed that weak interactions really do prefer one-handedness over the other. The universe, at least through the weak force, knows the difference between left and right. That discovery was shocking, and for neutrinos, it became crucial, because if the weak force only sees the left-handed neutrino, then a right-handed neutrino, if it exists at all, would be almost completely invisible to the standard model. It would not interact electromagnetically. It would not feel the strong force, and it would not participate in the weak force the way ordinary neutrinos do. It would be almost entirely hidden. That is why physicists sometimes call such a possible particle a sterile neutrino. Not because it is dead or inactive, but because it would be sterile to the known forces. And that possibility is deeply important, because if a right-handed neutrino exists, it could help explain why neutrinos have mass at all. And if it exists, it may also connect to much bigger mysteries, including the early universe and possibly even dark matter. So what first looked like a technical detail, handedness, turns out to be one of the most revealing cracks in the structure of modern physics. There is another question about neutrinos that makes them even stranger. Are neutrinos actually different from antineutrinos? For most particles, the answer is clearly yes. An electron and a positron are not the same thing. A proton and an antiproton are not the same thing. They carry opposite charges, and that difference makes them distinct. But neutrinos are different. They carry no electric charge. So the usual clean boundary between particle and antiparticle becomes much less obvious. That opens up a remarkable possibility. A neutrino might be its own antiparticle. If that is true, then the neutrino would belong to a very unusual class of particles known as Majorana particles. That would make it fundamentally different from particles like the electron, which are clearly distinct from their antiparticles. And if neutrinos really are Majorana particles, it would help explain one of the biggest mysteries about them: why their masses are so absurdly small. One of the leading ideas in theoretical physics, called the seesaw mechanism, suggests that the tiny mass of the neutrino we observe could be the visible consequence of an extremely heavy hidden partner. In that picture, the lighter the neutrino we can detect, the heavier the unseen partner state may be. That means the neutrino's tiny mass could be pointing toward physics at energies far beyond anything we can currently reach in particle accelerators. In other words, the neutrino might be giving us indirect access to conditions that existed in the very early universe. And that is why this question matters so much. Not because it is a naming detail, but because if the neutrino is its own antiparticle, it could change our understanding of what matter is at the deepest level. Right now, experiments are searching for a very rare process called neutrinoless double beta decay. If that process is ever observed, it would be one of the strongest signs that neutrinos are indeed their own antiparticles. So far, no confirmed detection has happened. But if it does, it would be one of the biggest discoveries in modern physics, because it would tell us that the neutrino is not just unusual. It is fundamentally unlike almost everything else we know. One of the most beautiful ideas in neutrino physics is also one of the simplest to imagine. It is called the seesaw mechanism. The basic thought is this: maybe the neutrino we observe is so incredibly light because it is connected to something incredibly heavy. Think of an actual seesaw on a playground. If one side is pushed very far down by a heavy weight, the other side rises very high. One side becomes large, the other becomes small. Their behavior is linked. The seesaw mechanism uses a similar logic. Instead of saying neutrinos are tiny by accident, it suggests their tiny mass may be the direct consequence of a hidden partner state with an enormous mass. That hidden partner would most likely be a right-handed neutrino, a particle that the standard model does not include in its visible structure, but that could still exist beyond it. And if such a particle exists, it would likely be almost impossible to detect directly with today's technology. Why? Because it would barely interact with ordinary matter at all. It would be even more hidden than the neutrinos we already know. But even if we cannot see that heavy partner directly, we may still be seeing its effect. That effect would be the tiny mass of the neutrinos we do observe. And this is where the idea becomes cosmologically important. If those heavy partner neutrinos existed in the early universe, they may have played a role in one of the biggest unanswered questions in science. Why does matter exist at all? Because in the early universe, matter and antimatter should have been produced in nearly equal amounts. And if they had perfectly balanced, they would have mostly annihilated each other. No stars, no planets, no atoms left over to build anything, no us. And yet matter won. Something created a slight imbalance, and some physicists believe that very heavy neutrino-like particles in the early universe may have helped create that imbalance through their decays. If that is true, then the reason anything exists tonight, the reason galaxies formed, the reason Earth formed, the reason you are here listening, may be connected to neutrino physics. That is an astonishing possibility. The lightest known particle may be quietly connected to one of the biggest reasons the universe contains anything at all. At first, neutrinos can sound like a niche topic. Tiny particles, hard to detect, interesting mainly to physicists. But the more closely you look, the more they begin to feel like one of the deepest clues in modern science. Because neutrinos are not just another entry on a particle chart. They sit at the edge of what we understand. They were first proposed to save one of physics' most trusted conservation laws. Then they turned out to interact so weakly with matter that it took decades to catch one directly. Then they revealed they could change flavor while traveling through space. Then they forced physicists to admit they have mass. Then they exposed a real limitation in the standard model. And now they continue to raise even bigger questions. Do hidden, sterile neutrinos exist? Are neutrinos their own antiparticles? Did neutrinos help create the matter-dominated universe we live in? Could they point toward entirely new layers of physics? That is why neutrinos matter. Not because they are dramatic in the ordinary sense, but because they are subtle in exactly the right way. They keep showing us that reality is deeper than our current theories can fully hold, and that makes them precious. In science, the most valuable particles are not always the ones we understand best. Sometimes the most valuable ones are the ones that refuse to fit, the ones that quietly force us to keep going. At this very moment, neutrinos are passing through your body. Not a few, not thousands, an unimaginable number. Most of them are coming from the sun. They were created in the nuclear furnace at its core, where hydrogen nuclei are constantly being fused into helium, releasing energy in the process. That energy eventually becomes sunlight and warmth. But long before the light reaches your skin, neutrinos are already on their way. Unlike light, which can spend thousands or even hundreds of thousands of years slowly working its way out from the sun's dense interior, neutrinos escape almost immediately. They barely interact with the solar material around them, so they leave the sun almost as soon as they are created. That means the neutrinos reaching you now are carrying near-direct information from the sun's core. In a way, they are messages from the center of a star. And they do not stop at the atmosphere. They do not pile up at the surface of the Earth. They pass through the whole planet with extraordinary ease. A neutrino can travel through thousands of kilometers of rock without interacting even once. Most of them pass through the Earth as if it were almost empty. And in a certain sense, for them, it is. That is one of the strangest things about neutrinos. They reveal that the apparent solidity of the world depends entirely on which interactions you are sensitive to. To you, a wall is solid. To a neutrino, it is almost transparent. To you, the Earth feels massive and impenetrable. To a neutrino, it is mostly just a region of space filled with matter it almost never notices. That changes the emotional texture of reality a little. It reminds you that the world is not just what it feels like to human senses. There are streams, structures, and hidden processes moving through everything all the time. And most of them pass unnoticed. So tonight, while you lie here in stillness, there is also movement. A constant invisible rain from the sun. Particles crossing your room, your skin, your bones, your bed, the floor beneath you and the whole Earth below. A silent cosmic traffic moving through everything you know. The sun is not the only source of neutrinos. It is simply the one closest to you. The universe is full of places that create them. Some neutrinos are born high above Earth's atmosphere. When cosmic rays, particles traveling across the galaxy at enormous speeds, crash into atoms in the air. Those collisions create showers of secondary particles, and among them are neutrinos. That means even the sky above you is quietly producing them. Other neutrinos come from radioactive processes inside the Earth itself. Deep below the crust, unstable elements slowly decay, releasing heat and producing what physicists call geoneutrinos. These particles rise up through the planet and out into space, carrying information about the hidden radioactive activity inside Earth's interior. In a strange way, neutrinos let us sense the planet from the inside out. And then there are far more violent sources. Supernovae, the catastrophic deaths of massive stars, release an enormous burst of neutrinos. In fact, when a star explodes as a supernova, most of the energy is not carried away by visible light. It is carried away by neutrinos. That means some of the most powerful events in the cosmos are, in a very real sense, neutrino events. When a massive star collapses, the core becomes so dense and extreme that neutrinos are produced in astonishing numbers. For a brief moment, the dying star releases a flood of them into space. And because neutrinos can escape dense environments so easily, they leave places that light often cannot. That gives them a special role in astronomy. light is powerful, but it can be blocked, scattered, trapped, or absorbed. Neutrinos are different. They can emerge from regions that would otherwise remain hidden. That is why physicists sometimes describe them as messengers from places that are normally inaccessible. The sun's core, the interior of collapsing stars, the deep earth, the high-energy collisions of the atmosphere, and perhaps even more ancient places still, because some neutrinos may have been traveling through the universe for billions of years, crossing galaxies, crossing voids, passing through worlds that formed and disappeared long before Earth existed. And now, after all that distance, some of them may be crossing through you tonight. Detecting a neutrino is one of the most patient things science does, because neutrinos are not rare. They are simply reluctant. They pass through detectors by the trillions, and almost all of them leave no trace at all. So if you want to catch one, you cannot rely on speed or force. You need scale, quiet, and time. That is why many neutrino detectors are enormous. Some are built deep underground, hidden beneath mountains or buried in old mines. Others are placed under ice, underwater, or near nuclear reactors. The goal is always the same: create a place quiet enough that when one neutrino finally does interact, you can notice it. Because that interaction, when it happens, is tiny. A neutrino may collide with an atomic nucleus or an electron inside the detector, and that rare event can produce a flash of light or a secondary particle moving through the detector material. The detector is not seeing the neutrino directly, like a camera sees a bird in the sky. It is seeing the effect of one rare moment when the neutrino finally touches matter strongly enough to leave evidence behind. That is how much of particle physics works. You do not always observe the thing itself in the ordinary sense. Sometimes you observe what it causes. Some detectors use giant tanks of purified water. Others use heavy water. Others use liquid scintillator, ice, or specially chosen chemicals that react in useful ways when struck by certain particles. Each detector is like a listening device built for a whisper. And because neutrinos are so difficult to catch, every confirmed interaction matters. Each one is a tiny message. A trace from the sun, a trace from a reactor, a trace from the atmosphere, a trace from a distant cosmic event. And when enough of those traces are collected, patterns emerge. Oscillations, flavor changes, energy distributions, directional clues. And from those patterns, physicists slowly reconstruct the hidden behavior of one of the most invisible particles in the universe. That is part of what makes neutrino science feel almost meditative. It is not about forcing nature to reveal itself loudly. It is about building a place quiet enough that the faintest truth can finally be heard. One of the strangest things about neutrinos is not just that they pass through matter. It is how easily they do it. A neutrino can cross enormous distances through solid material without interacting even once. Rock, water, metal, ice, flesh, entire planets. To a neutrino, most of it is almost irrelevant. That feels unnatural because matter seems dense to us. It feels packed, substantial, resistant, but that is only because we live through forces that neutrinos mostly ignore. The world feels solid to you because electromagnetism dominates your experience. The atoms in your body repel the atoms in a wall. Electron clouds resist overlap. Surfaces push back. Light reflects. Matter holds shape. That is the world as experienced by charged particles like electrons. But neutrinos are not wired into the world that way. They carry no electric charge. so electromagnetism does not grab them. They do not carry the kind of charge needed for the strong force either. So the force that binds quarks inside protons and neutrons mostly ignores them too. That leaves almost everything dependent on the weak force alone. And the weak force, true to its name, gives neutrinos only a tiny chance of interacting as they pass through matter. That means the neutrino is not really drilling through the Earth the way a bullet drills through wood. It is not smashing through resistance. It is simply moving through a world that, from its point of view, barely offers any meaningful way to respond. That is a profound reminder that what counts as real or solid depends on the kind of particle you are. A wall is not absolutely solid. It is only solid to things that couple strongly enough to feel it. To you, the Earth is massive and closed. To a neutrino, it is mostly transparent. And once you understand that, the universe starts to feel a little less fixed. Matter is not one universal experience. It is a relationship, and neutrinos live in a very different version of that relationship than we do. If neutrinos are this strange today, it is natural to wonder what role they played when the universe was still young. And the answer is probably a very important one. In the first seconds after the Big Bang, the universe was unimaginably hot and dense. Particles were not arranged into atoms, stars, or galaxies yet. Everything was still part of a rapidly expanding, high-energy cosmic plasma. In that early environment, neutrinos were not rare side effects. They were part of the main structure of reality. They were being created, destroyed, and scattered constantly in the intense heat of the newborn universe. At those energies, they were much more tightly connected to everything around them than they are today. But as the universe expanded and cooled, something changed. The particles slowed. The density dropped. And eventually, neutrinos stopped interacting often enough to remain in thermal contact with the rest of matter and radiation. They effectively decoupled from the rest of the universe. And once that happened, they began free streaming through space, almost untouched. That means there should still be an ancient background of relic neutrinos left over from the early universe. A kind of neutrino equivalent of the cosmic microwave background. A faint sea of primordial neutrinos still filling the universe today. We have not directly detected that cosmic neutrino background yet. It is extraordinarily difficult to measure, but the theory strongly suggests it should be there. If so, then the universe around you is not only filled with neutrinos from the Sun, the Earth, and distant cosmic events. It may also be filled with neutrinos that have been traveling since the first moments of cosmic history. Particles older than stars, older than galaxies, older than Earth. Still here, still passing through everything. That thought gives neutrinos a different emotional weight. They are not just products of astrophysical processes. They may be among the oldest surviving messengers in existence, a quiet relic of the universe's beginning, still moving through the darkness tonight. There is a possibility in modern physics so large, it almost sounds fictional. The existence of matter itself may be connected to neutrinos, not stars specifically, not atoms specifically, matter as such. Because when physicists try to reconstruct the earliest conditions of the universe, they run into a very serious problem. The laws of physics suggest that matter and antimatter should have been created in nearly equal amounts. And if that had happened perfectly, then almost all of it would have annihilated. Matter and antimatter destroy each other when they meet, converting into energy. So if the early universe had been exactly balanced, there should have been almost nothing left. No galaxies, no planets, no chemistry, no life. No one here to ask the question. And yet, clearly, that is not what happened. Matter survived. Somehow, the universe ended up with a slight excess of matter over antimatter. And that tiny imbalance changed everything. It is one of the most important unsolved questions in cosmology. Why did matter win? One possible answer involves neutrinos. More specifically, very heavy neutrino-like particles that may have existed in the early universe. If those particles behaved slightly differently from their antimatter counterparts when they decayed, they could have created a small asymmetry, just enough to tilt the universe away from perfect balance. That idea is called leptogenesis. And if it is true, then the neutrino is not just a strange particle on the edge of the standard model. It is part of the reason there is a world at all. That is one of the reasons neutrino physics matters so much. It is not just about tiny particles in underground detectors. It may be tied directly to why reality did not cancel itself out before stars ever formed. So when physicists study neutrinos, they are not only studying what matter is made of, they may also be studying why matter was allowed to remain. There is something almost poetic about the neutrino, not because it is romantic or dramatic, but because it keeps revealing deep truths through absence rather than force. It was first noticed because energy seemed to be missing. Then it remained invisible for decades after it was proposed. Then it turned out to pass through matter, almost untouched. Then it quietly changed identity in flight. Then it exposed a flaw in the standard model. And now it may be connected to the earliest moments of the universe and the existence of matter itself. At every stage, the neutrino has taught physics something important, not by being loud, but by refusing to fit neatly into what we expected. That is a beautiful pattern. Some parts of reality are obvious: bright stars, explosions, galaxies, black holes. Neutrinos are not like that. They belong to the quieter side of the cosmos, the hidden side, the side that only appears when your instruments become sensitive enough, your theory becomes precise enough, and your patience becomes deep enough. That makes them perfect for a certain kind of wonder. Not the wonder of spectacle, but the wonder of hidden structure. The wonder of realizing that the universe is not exhausted by what is visible. That even now, in the quiet of your room, there are ancient particles moving through you that almost no part of the material world can feel. And yet, they are real. That is the neutrino's strange gift. It reminds us that some of the deepest truths in nature do not arrive with noise. They arrive as silence that turns out to mean something. So tonight, as you lie here in the dark, the neutrino becomes something more than a particle. It becomes a reminder that the universe is far stranger than it first appears, that the world around you, the room, the walls, the ground beneath you, the planet itself, is not a sealed and solid stage in the way it seems. It is a place continuously crossed by invisible motion, by ancient messengers, by particles born in stars, in reactors, in collapsing suns, in the early universe itself, and most of them pass through unnoticed. The neutrino does not force itself into your attention. It does not shine. It does not roar. It does not demand to be seen. And yet, it may carry some of the deepest clues we have about how reality is built, why energy stays balanced, why the sun works, why particles have mass, why the standard model is incomplete, why matter may have survived at all. All of that hidden inside one of the quietest particles in existence. And maybe that is part of what makes the universe feel so beautiful at night. Not just that it is large, but that it is layered. That beneath the visible sky, beneath the stars, beneath the atoms of the world around you, there are still deeper structures moving in silence, carrying stories we are only beginning to understand. So if this journey through neutrinos helped quiet your mind, slowed your thoughts, or gave you that strange, peaceful feeling that comes from staring into the hidden architecture of the cosmos, then stay close to the channel, because there is always more out there, more mysteries, more strange particles, more invisible forces, more beautiful questions waiting in the dark. Sleep well. And if you want more calm journeys through the universe before sleep, stay here with Science Theory. There is always another mystery waiting beyond the next star.